All right, welcome to the class. Today we're going to have a look at the second part of C2L1. We're going to talk about Newton's laws of motion today. So Newton's laws of motion are these three separate statements that explain how and why objects move or stay at rest. When a player hits a puck on the air hockey table, as shown here in figure 1, Newton's laws describe what happens to the puck before, during, and after the collision with the paddle. Newton's laws also describe the forces the objects exert on each other. You can use these three laws to explain the motion of many types of objects, experiencing and exerting different types of forces. Okay, so first let's have a look at Newton's first law of motion. If you watch a puck move across the air hockey table, you'll notice that it moves at a relatively constant velocity. This is because the puck floats on a cushion of air and moves with little friction acting on it. In fact, the net force on the puck is virtually zero. In addition, when the puck is at rest and no one hits it, the puck will remain at rest. This example demonstrates Newton's first law of motion. Okay, so Newton's first law of motion states that if the external net force on an object is zero, the object will remain at rest or continue to move at a constant speed. Constant velocity. Some important implications of Newton's first law of motion are the following. First, a net force is not required for an object to maintain constant velocity. Second, a net force is required to change the velocity of an object in magnitude, direction, or both. Third, external forces are required to change the motion of an object. Internal forces have no effect on an object's motion. Okay. Next, let's have a look at the concepts of inertia and mass. Galileo introduced the concept of inertia, and Newton used this concept to develop his first law of motion. Inertia is a property of matter that causes an object to resist any changes in motion. This means that an object at rest will stay at rest unless a net force acting on it. In addition, if an object is in motion, it will maintain a constant velocity unless a net force acts on it. The concept of inertia is closely related to Newton's first law. So inertia means a measure of an object's resistance to change in velocity. Some objects have more inertia than others. In fact, objects that have more mass have more inertia. The degree to which an object resists a change in motion depends on the magnitude of the object mass. Mass is a measure of the amount of matter in an object. The SI unit for mass is kilogram. Objects that contain a small amount of matter have a smaller mass and less inertia than objects that contain a large amount of matter. For example, a basketball has a mass of approximately 0.62 kilograms, and a volleyball has a mass of approximately 0.28 kilograms. If you hit each one with an equal force, the heavier ball, which is a basketball, changes its motion less than the lighter ball, which is a volleyball. Inertia is directly proportional to the mass of the object, where a mass is actually a measure of the amount of matter in an object. Okay, so that's Newton's first law of motion. Next, let's have a look at Newton's second law of motion. Newton's second law of motion explains the relationship between mass, acceleration, and net force. It states that if the net external force on an object is not zero, the object will accelerate in the direction of the net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the object mass. The acceleration of an object with mass m is then given by the acceleration equals the net force over the mass of the object. Then Newton's second law is often written in the equivalent form. The net external force sigma F equals mass m times acceleration vector A. So recall from section 2.1 that the net force or total force on an object is the sum of all the individual external forces. The external force equals total force F equals the sum of all external forces. In most cases, more than one force acts on an object at any given time. To determine the total force, we add all these forces together. That resulting vector sum is the force sigma F in Newton's second law, as shown here in figure 2. Newton's second law, sigma F equals m times acceleration A, indicates that the acceleration of an object A is always parallel to the net force, sigma F, acting on the object. However, since acceleration and velocity might be in different directions, velocity and net force need not be in the same direction. For example, you can be moving forward in a car while applying the brakes. You and the car are still moving forward, but you are accelerating backward. Okay, we can write Newton in terms of the SI units for mass, which is kilograms, and acceleration, which is meters per second squared, which is sigma F equals ma. Well, this implies Newton equals kilograms times meters per second squared, right? So the value of the Newton as a unit of force is therefore 1 Newton equals 1 kilogram times 1 meters per second squared. Okay, so next let's have a look at a tutorial which shows how we can use equation for Newton's second law of motion to predict how several different forces act on an object. Okay, so let's have a look at tutorial 1, solving two-dimensional problems using Newton's second law. Okay, sample problem 1, calculating acceleration and direction. So we have two tugboats here, which are pulling a 4.2 times 10 to the power of 3 kilograms barge into a harbor, as shown here in figure 3. The first tugboat exerts a constant force of 1.8 times 10 raised to the power of 3 newtons. Direction is 37 degrees north of east. The second tugboat exerts a constant force of 1.3 times 10 raised to the power of 3 newtons, and the direction is 12 degrees south of east. Can you calculate the acceleration, which include both magnitude and direction of the barge? Assume there is no friction acting on the barge. All right, I'll give you 10 minutes to think about this question. And then we'll have a look at the solution together, okay? Okay, so let's have a look at the solution here. So in this question, we are given the following information. First of all, the mass of the barge is 4.2 times 10 to the power of 3 kilograms. And force F1, the magnitude of force F1 is 1.8 times 10 raised to the power of 3 newtons. And magnitude of force F2 is 1.3 times 10 raised to the power of 3 newtons. And according to this diagram, we have two angles. One of them is 37 degrees. The other one is 12 degrees. So we can let theta 1 is 37 degrees north of east, and theta 2 is 12 degrees south of east. So we need to find the acceleration of the barge A and the angle at which the barge moves theta. Okay, so we can denote the north and east as positive for components, then break the force into its components using sigma fx equals f1 times cosine theta 1 plus f2 times cosine theta 2. And do the same thing for the net forces along the y directions. Then we can draw an FBD, free body diagram. And then use the arc tangent to determine the direction of the force. And use magnitude of the net force equals the square root of the squared fx component plus squared y component to calculate the magnitude of the force. And then using the net force equals m times acceleration a to calculate the acceleration. So we can draw the FBDs here as shown in these three graphs. Then we can resolve the two forces in the x and y axis. You can find sigma fx equals 2.7 times 10 raised to the power of 3 newtons, and sigma fy equals 8.13 times 10 raised to the power of 2 newtons. The direction of the force is theta equals 17 degrees. Then the magnitude of the force is a square root of squared x component plus squared y component. And this gives us 2.82 times 10 raised to the power of 3 newtons. So the acceleration of the barge is A equals net force over the mass of the barge. Put all the values in, we have the acceleration is 0.67 meters per second, per square second, and direction is 17 degrees north of east. Then we can make the statement here, as shown here in bottom right. The acceleration of the barge is 0.67 meters per square second. Direction is 17 degrees north of east. Okay, any questions? No? All right, then let's have a look at Newton's third law of motion. Remember, we have mentioned there are 3 laws, right? Next, let's have a look at Newton's third law of motion. Newton's first 2 laws of motion deal with a single object and the forces acting on it. Then the third law of motion deals with forces that 2 objects exert on each other. So Newton's third law of motion states that for every action force, there exists a simultaneous reaction force that is equal in magnitude, but opposite in direction. So Newton's third law is also known as the action-reaction principle. For example, if you push east on a wall, the wall exerts a simultaneous force west on you, causing you to move away from the wall. Newton's third law states that action-reaction forces always come in pairs. According to Newton's third law, these 2 equal and opposite forces must always act on different objects. Next, let's have a look at another tutorial in which we'll use the equation for Newton's second law of motion to demonstrate Newton's third law of motion. Okay, now let's have a look at this tutorial, solving problems related to Newton's third law. Okay, sample problem 1, which is to calculate acceleration due to Newton's third law. So here's a person on rollerblades in figure 4 is pushing on a refrigerator that sits on a cart on a level floor. Assume no force of friction exists on either the person or the refrigerator. The person has a mass of 60 kilograms and the refrigerator has a mass of 1.2 times 10 raised to the power of 2 kilograms. The force exerted by the person on the refrigerator is 1.8 times 10 raised to the power of 2 newtons with direction forward. Can you calculate the refrigerator's acceleration and the person's acceleration? Okay, so note here acceleration has both magnitude and direction. Okay, I'll give you 5 minutes to have a look at this problem by yourself, and then we'll have a look at the solution together. You can start now. Right? Have you finished? Okay, let's have a look at the solution together. Okay, in this question, we are given the following information. We know the mass of the person is 60 kilograms, and the mass of the refrigerator is 1.2 times 10 raised to the power of 2 kilograms. And the applied force of the person on the refrigerator FA is 1.8 times 10 raised to the power of 2 newtons with direction forward. And we are going to find the acceleration of the refrigerator and the person, a person. So the forces acting on the refrigerator are gravity and the normal force, and force applied by the person on the refrigerator. The floor is level, so gravity and normal forces cancel each other, right? So we can use Newton's second law to determine the refrigerator's acceleration. So note here the net force is just the applied force of the person on the refrigerator. So the refrigerator's acceleration A can be given by net force F over the mass of the refrigerator. Use the same equation to determine the person's acceleration. The action force of the person on the refrigerator is equal to the reaction of the refrigerator on the person in magnitude, but opposite in direction. This is according to Newton's third law of motion, right? Okay, so we can find the acceleration of the refrigerator using 1.8 times 10 raised to the power 2 newtons is direction forward, divided by the mass of the refrigerator, which is 1.2 times 10 raised to the power 2 kilograms. Then we can find the acceleration of the refrigerator is 1.5 meters per square second with direction forward. Then using the same method, we can find the acceleration of the person is 3.0 meters per square second with direction backward. Or if you specify the positive direction is forward, you can also say that the person's acceleration is -3 meters per square second. Okay, so we can make the final statement. The acceleration of the refrigerator is 1.5 meters per second with direction forward, and the acceleration of the person is 3 meters per square second with direction backward. Okay, any questions? Okay, good. If no questions, let's have a look at another concept, which is the gravitational force. Earth's force of gravity is something you are quite familiar with from everyday life, right? However, Newton realized that gravity is an attractive force between all objects, including the motion of the planets and stars. As mentioned in section 2.1, the gravitational force is weak when the objects are far apart and or small. However, Earth is so much more massive than any other nearby objects that the strongest gravitational attraction on objects around you is toward Earth. You know that if you allow an object to fall, it will accelerate downward. In the absence of air resistance, the acceleration due to gravity near the Earth's surface varies depending on the distance from the Earth's surface. At or near Earth's surface, the acceleration due to gravity is 9.8 meters per square second with direction down. When the object is in free fall, when an object is in free fall, it is moving toward Earth with only the force of gravity acting on it. In other words, we are assuming that air resistance is negligible. Okay, next, let's have a look at weight and the normal force. So according to Newton's second law, when an object is in free fall, the net external force sigma F equals m times acceleration a, right? Where acceleration a is a acceleration due to gravity, g. Since the only force acting on an object is gravity, we have sigma F equals Fg. Therefore, the force of gravity is given by Fg is m times the acceleration due to gravity, lowercase g. Another name for gravitational force is weight. The weight Fg of an object is a force that is therefore measured in newtons. It is often convenient to indicate a force that is directed downwards by making the force negative. So when solving problems, you will often use Fg equals negative m lowercase g. The negative sign here indicates that the force is in the negative y direction or down toward the center of Earth. As you can see here in figure 5, which is shown in bottom left, in addition to the gravitational force, another force acting on a person is the normal force exerted by the floor on her feet. The person in figure 5 is at rest with an acceleration of 0. Using Newton's second law for components of the force and acceleration along y, we can see that sigma F equals negative mg plus Fn. Fn is normal force. Then sigma F equals ma, right? So put ma there, we can have 0 equals negative mg plus Fn. Then we have Fn equals mg. So this means the normal force is equal in magnitude and opposite in direction to the person's weight in this case. This raises two common misconceptions in physics, which need to be cleared up at this point. First, the normal force is not the reaction force to gravity. The reaction force to the force of gravity is another force of gravity. The normal force is the reaction force to the object applying a force to the surface. Second, since the normal force is not the reaction force to gravity, the normal force is not always equal in magnitude and opposite in direction to the force of gravity. For example, if someone pushed down on the shoulder on the person in this figure, the normal force would increase, but the force of gravity on the person remains the same. If the person in this figure were standing on a ramp, the normal force would be perpendicular to the ramp and no longer vertical, but gravity would still point straight down. These are the 2 points you need to be careful with, okay? All right, so these are the major topics we have talked about in the second half of C2L1. Do you have any questions? If not, please remember to complete your homework on Google Classroom and submit them before the deadline, okay? I'll see you next time.